Hello everybody and welcome to example 1. We are looking at page 17 of the workbook. This is our first example to kind of examine what we mean by the definition of a span of a set of vectors. Okay, so let's start with part A here. It defines a set W1 to be the span of the single vector 2, 1. Okay, so let's remind ourselves of what the idea of a span was. Okay, so the span of a set is the set of all possible linear combinations of the vectors in the set. So this is like asking us, what are all of the things that we can build using just the single vector 2, 1? Okay, well, since there's only one vector in the set, the only thing we can do to form a linear combination is just to take scalar multiples of that. Okay, so by definition, the span of 2, 1 is just going to be the set of all scalars a times 2, 1, where a could be any real number that we want it to be. Okay, and we could ask the question, what are some vectors that are in that span? Okay, well, we just need to choose some values of a. So how about if we start with a nice first number, a equals 0. Well, if we let a equal 0 and take 0 times 2, 1, we're just going to get the 0 vector. That's one vector that's in the span of this set. Okay, how about a equals 1? Okay, if we choose a equals 1, then this thing I'm underlining is just going to be 1 times 2, 1. That's 2, 1. Okay, we can keep doing this with any value of a that we want. So how about a equals negative 1? Okay, negative 1 times 2, 1 would just give us negative 2, negative 1. Okay, and we'll, just to make it interesting, let's throw in a non-whole number. So how about a equals a half? Okay, well, a half times 2, 1 would just be 1 and 1/2. Okay, and this process can be continued indefinitely. Okay, now they ask us to also give a graphical description of these. Okay, so let's plot the points that we've generated so far. So starting with 0, 0, that's right here at the origin. Then we come to 2, 1, that's over here. And then negative 2, negative 1, that's down here. And then finally 1 and 1/2. And I'm wondering if you notice anything interesting about the pattern of points that we're generating here. Notice that they all lie on a line. Okay, and that line in R2 is the set W1 that we're talking about. Okay, so let's make a couple of observations here. So first, kind of what we did to get the vectors in W1, we just took scalar multiples of 2, 1. Okay, so W1 is the set of all scalar multiples of 2, 1. Okay, and then we noticed that graphically, that set yields a line in R2. Okay, so there's our first example. And let's move on to part B here, which asks us to calculate a different span. This time we'd like to calculate W2, which is defined to be the span of the two vectors, 1, 2, and negative 2, negative 1. Okay, and again, span is all about asking, what are all of the vectors that we could build using these as our building blocks? Okay, so all possible linear combinations that we can make with those two vectors. Okay, and so if we write this out algebraically, I'm going to go to the next line just so this doesn't get too cluttered here. Okay, the set of all linear combinations of those two vectors would look like a scalar times the first one plus a scalar times the second one. Okay, and then those two scalars, a1 and a2, can be any real number that we want. Okay, we can do the same thing that we did in the example above and just ask, okay, what are some vectors that would live in this set that we just wrote down? Okay, so now let's start with some easy values like we did before. So if we made a1 and a2 both 0, okay, then we're just going to get 0 times 1, 2 plus 0 times negative 2, negative 1. That's going to give us 0, 0. Okay, and then how about a1 equals 1 and a2 equals 0? What would happen then? Okay, well, if we go up here, you substitute in 1 for a1 and 0 for a2, you're just going to get the first vector in our set, 1, 2. Okay, I'm going to keep going just with a couple of combinations here. So what if we chose a1 to be 0 and a2 to be 1? Okay, well, if we do that, we're going to get the second vector on our list. The first one's going to disappear, so we'll just get -2, -1. Okay, and I'm going to just choose two more combinations. So we could maybe choose a1 and a2 both to be 1, and then a1 to be 2 and a2 to be 1. Let's just see what happens with those two choices. Okay, so if a1 and a2 are both equal to 1, then this thing I'm underlining is just going to become 1, 2 plus -2, -1. If you do that arithmetic, you're going to get -1, -1 positive 1. Okay, and then you can double check my arithmetic here for the last one, you're going to get 0, 3. Okay, and that process would continue. Okay, let's plot those points and just see what they look like this time. Okay, so we've got 0, 0. 1, 2 is up here. -2, -1. Okay, that's down here. -1, 1 is up here. And then finally 0, 3 is up here. Okay, so what do you think? If we kept doing this, kind of substituting in more and more values of a and plotting more and more points, what do you think would happen? Okay, well, if you did this experiment, you could probably convince yourself that we can get any point we want in R2 if we choose the A1 and the A2 right. Okay, so in fact, W2 is all of R2. Okay, now we're not going to prove that, but let's just write down what that's really saying algebraically. It's like saying that if somebody just handed you a totally arbitrary vector in R2, we're saying that it should be possible to build that vector AB using a linear combination of 1, 2, and -2, -1. Okay, if we take this a step further, okay, just simplify this expression that we wrote down, we can rewrite it like this. A1 minus 2a2, 2a1 minus a2. I'm just kind of taking that left-hand side and simplifying it. It has to be equal to ab. And what's kind of interesting about this equation is that you can rewrite it as a system of equations. So this has to equal that. The two first coordinates have to equal each other. And the two second coordinates have to equal each other. And so what we're saying with the claim that we're making here, we're not proving this claim, but what we're saying is that this system of equations can always be solved no matter what a and b are equal to. Okay, so this brings up kind of an issue that we're going to see in the future problems that we do. Working with or figuring out what the span of a set of vectors is often comes down to working with systems of equations, and so future examples will get started talking in a little bit more detail about that.